is the Large Hadron Collider, or LHC for short. It might sound like something out of science fiction, and honestly, it kind of is. This machine is essentially a giant racetrack, but instead of cars, it smashes subatomic particles together at nearly the speed of light. Pretty mind-blowing. Think of it this way, the LHC is like a time machine, allowing us to see what the universe might have been like just after the Big Bang. It's a marvel of engineering, a massive ring stretching 17 miles wide and buried a whopping 175 meters underground. And it's not just in one country but built in collaboration between France and Switzerland, displaying international teamwork in the pursuit of scientific discovery. This scientific powerhouse comes with a hefty price tag, though. The LHC cost a cool $4.5 billion to build and even more to maintain and upgrade. But the payoff has been significant, helping us unlock secrets of the universe at its most fundamental level. So how does this wonder machine work? It's all about velocity. The LHC whips subatomic particles around its track until they are practically flying at the speed of light, making thousands of laps per second. How do they achieve such incredible speeds? With the help of incredibly powerful electromagnets generating a magnetic field thousands of times stronger than Earth's own. Now, some folks were understandably worried about the impact of such a strong field on nearby electronics and even the planet's magnetic balance, but that's just the setup. Once these particles reach their top speed, nearly 1,000,000 times faster than sound, they smash into each other head-on. That's what the LHC is designed to do, and it's this collision that scientists are truly interested in. It's through these collisions that we hope to learn more about the fundamental building blocks of our universe. The crash between these particles is no joke, it unleashes a huge burst of energy, spawning a whole bunch of different subatomic particles. These new particles scatter in all directions, but they're like fireworks, here one minute, gone the next. Most of them disappear almost instantly. Fascinatingly, by changing up the types of particles they smash together, scientists can potentially discover entirely new particles hiding within the mayhem of the collision. To capture these fleeting moments, they've built incredibly sensitive detectors around the collision points. Think of these detectors as superpowered cameras recording every detail of the crash. The only problem? All this action creates a massive amount of data, over 15 petabytes every year. That's like having a whole library of information dumped on you every single year. Sifting through all this data takes some serious time and effort, but within this treasure trove lies the key to unlocking some of the universe's biggest mysteries. The LHC has already achieved something remarkable. It's challenged our current understanding of the universe, shaking things up in the world of physics. Ever wondered how the universe works? Scientists have this amazing blueprint called the Standard Model, kind of like an instruction manual for everything in the universe. It explains how all the tiny building blocks, like quarks and electrons, interact with each other, almost like following directions to build a Lego set. The Standard Model is pretty impressive, describing everything from the tiniest particles to the forces that hold them all together. There are these things called quarks, for instance, and they come in 6 different flavors, each with its own unique properties like electric charge and mass. Then there are leptons, like electrons, which are essential for building atoms. And don't forget the bosons, the busy bees that carry forces like electromagnetism and act as the glue holding quarks together. But here's the catch, the Standard Model, for all its brilliance, isn't entirely complete. It leaves some big questions unanswered. That's where the LHC comes in. By recreating powerful collisions like the Big Bang, it's uncovering mysteries that our current understanding can't explain. Take a particle called the beauty quark, for example. The LHC's findings are challenging our entire picture of the universe in unexpected ways. Scientists made a surprising discovery: when beauty quarks break down, they don't quite follow the rules laid out by the Standard Model. According to the predictions, these quarks should change into muons and electrons at similar rates, but experiments at the LHC showed something different. This unexpected twist suggests there might be entirely new particles or forces at play, which goes against our current understanding. And that's not all. The LHC's collisions are also producing bizarre particles that the Standard Model can't account for. One such example is the pentaquark, a whole new kind of particle made up of 5 quarks instead of the usual 3 found in protons and neutrons. This discovery of the pentaquark is a significant development, opening doors to a whole new world of possibilities. It suggests the existence of previously unknown quark combinations just waiting to be unearthed. But the truly exciting aspect lies in its implications for our comprehension of the universe. The pentaquark hints at the presence of mysterious subatomic forces that we are only beginning to grasp. The discovery of the pentaquark was a groundbreaking moment. The statistical deviation observed was a remarkable 15 sigma, showing the LHC's incredible precision and power in the world of particle physics. Achieving a deviation of 5 sigma is considered the gold standard for confirming a particle's existence, so a deviation of 15 is truly exceptional. And the surprises didn't stop there. The LHC also discovered another exotic particle, the tetraquark, further challenging the standard model. This 4-quark wonder, named TCC+, is one of the latest additions to the world of particles. Think of it as a quartet of quarks, with 2 heavier charm quarks and 2 lighter ones, all bound together by the strong nuclear force. Similar to the pentaquark, its discovery suggests the existence of even more quark combinations waiting to be explored. Interestingly, the TCC+ holds the potential to unlock the secrets of quantum chromodynamics, QCD, for short. These are the fundamental rules governing how quarks interact under extreme conditions, and they form a crucial piece of the standard model. It's a complex puzzle, but broadening our understanding of QCD could lead to groundbreaking discoveries about the very nature of matter itself. The LHC detector played a pivotal role in uncovering the tetraquark. Scientists were able to catch a fleeting glimpse of the TCC+'s signature amidst the chaos of proton collisions. However, the TCC+ is a short-lived entity, much like a fleeting spark before it transforms into other particles. In a surprising turn of events, the LHC revealed that the Higgs boson, a critical piece in our understanding of the universe, is heavier than initially predicted. But what exactly is this elusive particle? The Higgs boson, often formally called the Higgs particle, is a fundamental building block within the standard model of particle physics. It arises when the Higgs field, another cornerstone of particle physics theory, becomes agitated through a process known as quantum excitation. Within this model, the Higgs boson reigns supreme in terms of mass. It's a scalar boson, meaning it has no spin, a positive intrinsic parity, but lacks electric or color charge. However, its existence is fleeting. It rapidly decays into other particles almost immediately after formation. Now let's look deeper into the concept of the Higgs field. Imagine an invisible field spreading out over the entire universe. This field possesses a unique characteristic: it always holds a non-zero value, even in the vast emptiness of space. This property, through a mechanism known as the Higgs mechanism, is responsible for imbuing various particles with mass. Think of it metaphorically: the Higgs field throws a universal party, inviting all the particles to join. The interaction during this party gives mass to the particles while breaking a fundamental symmetry of the universe. We owe this profound insight to physicist Peter Higgs and his colleagues, who proposed the ingenious Higgs mechanism in 1964. This groundbreaking theory not only explained how particles acquire mass but also predicted the existence of the Higgs boson itself. It's like solving a complex puzzle. If their theory holds true, a particle with specific characteristics must exist, and voila! The discovery of the Higgs boson beautifully corroborated their predictions. The Higgs boson, often nicknamed the God particle, finally emerged from a 40-year scientific quest in 2012. Scientists at CERN, using the powerful ATLAS and CMS detectors within the LHC accelerator in Switzerland, unearthed this long-sought-after particle, perfectly matching the predicted properties of the Higgs boson. The discovery of the Higgs boson was like finding that crucial missing piece. The significance of this breakthrough was undeniable, leading to the Nobel Prize in Physics being awarded in 2013 to Peter Higgs and François Englert, 2 key figures behind the Higgs mechanism theory. However, it's important to acknowledge the collaborative nature of this achievement. Several researchers, independent of each other, contributed crucial pieces to the puzzle between 1960 and 1972, laying the groundwork for what would become known as the Higgs mechanism. Fast forward to recent times, with the LHC accumulating more data. Scientists made a surprising discovery about the Higgs boson. Its mass was found to be greater than 125 gigaelectron-volts per square speed of light. This revelation sent shock waves through the scientific community. A heavier-than-predicted Higgs boson could necessitate a re-evaluation of our fundamental understanding of the universe. Does this mean we need to scrap the Standard Model entirely? Not necessarily, but it certainly hints at the possibility of new particles or forces existing beyond our current knowledge. It's like discovering a completely new puzzle piece, one that could potentially revolutionize our perspective on the universe. Furthermore, the heavier Higgs boson has spurred renewed exploration of the Higgs field itself and how it interacts with other particles. It also led to discussions around the potential existence of supersymmetry, a theoretical framework proposing that each particle has a partner. As physicists continue to unlock secrets within the realm of particle physics, they are also working to reconcile how these discoveries tie into cosmic phenomena. Have you ever wondered why the universe is expanding? There's a mysterious force known as dark energy responsible for this expansion, yet we don't fully understand it. By pushing the limits of our understanding of particles through experiments at the LHC, researchers aim to unravel the enigma of dark energy and its connection to the Higgs field. The interplay between the Higgs boson, dark energy, and the fabric of spacetime could offer valuable insights into the ultimate fate of our universe. The LHC stands as a beacon of hope in the world of physics, a marvel of human ingenuity that brings us closer to understanding our universe's mysteries. As we continue our quest for knowledge, we inch closer to answers to some of our most profound questions. While the journey has just begun, the discoveries made at the LHC challenge our perceptions of the universe, encouraging future generations of scientists to push the boundaries of human knowledge. The wonders of the universe await us, just a collision away.